A 400 Newton meter spring is connected to a 4 kilogram block, and the block slides horizontally with negligible friction. We chose a coordinate system where x equals 1 centimeter is the equilibrium location. The block is initially held at x equals 0 centimeters at rest when it is kicked to the right. The maximum value of x attained by the block is x equals 5 centimeters. So for part A, it's how much energy is transferred to the block by the kick. So because it starts at 0 centimeters and the equilibrium is at 1 centimeter, you have to find the energy before the spring. So it's 1/2 400 Newton meters times 1 centimeter, which is 0.01 meters squared, and you get 0.02 joules. Then you find the energy from the spring, and it travels 0.04 meters because it goes 4 centimeters because it starts at 1 and goes to 5. Plug that into 1/2 kx squared and you get 0.32 joules. You subtract the initial energy here, 0.32 minus 0.02, and you get the energy from the kick is 0.3 joules.
Okay, so for part B, we're trying to determine the position of the block as a function of time in terms of this general wave function. And A represents the amplitude, which we know is 4 centimeters since the max value attained by the block is 5 centimeters and the equilibrium was at 1 centimeter, so 5 minus 1 equals 4. We know that D, the offset, is equal to 1 since the block starts at 0 centimeters and its equilibrium is at 1 centimeter. And then in order to find omega, we take the square root of k divided by m. K is the spring constant and m is the mass of the block. So k equals 400, m equals 4. So root 400 over 4 is equal to 10, and that's in units of radians per second. So in order to find phi, we have to plug in all the known values at t equals 0, and at t equals 0 the position is 0. So once we solve for t, we will get phi equals negative 0.0804 pi, and so we plug everything into the general wave function and we get that.
Okay, so part C is what is the velocity of the block the first time it is located at x equals -1 centimeters. So to figure this out, we're going to set the total energy of this system is equal to the kinetic energy plus the potential energy, and the total energy we know is 0.32 joules because we already calculated that in part A. Then you set that equal to 1/2 mv squared plus 1/2 ka squared. So next we're going to want to figure out the potential energy at 2 centimeters displacement from the equilibrium, because that's the point that we're trying to find the velocity at. So we're going to set 1/2 times 400 Newton meters times 0.02 meters squared, and we get 0.08 joules as the potential energy. And now you take the total energy and subtract the potential energy of 0.8 joules from it, and you get 0.24 joules kinetic energy. And then you just set the 0.24 joules equal to 1/2 mv squared, and we solve for V, and V is 34.6 centimeters per second.